In this video, I'd like to talk about motional EMF. We've been talking about Faraday's law and how an EMF is induced when the magnetic flux through a loop is changing. So in this section, we can see that an EMF is also induced if a conductor is going to be moving in an external magnetic field. Let's see what happens. So in this picture, we have a conductor, so some kind of metal that is moving to the right here, and there's an external field into the page. FB here is the magnetic force acting on a positive charge in the conductor. It's upward using the right hand rule. If you remember the right hand rule that I call right hand rule number 3, you put your fingers in the direction of V, so your hand is going to look like this. And the reason I know that the hand is like this is because you have to fold the fingers in the direction of B. So if you've got your palm facing away from you, then you can fold your fingers into the page here, and your thumb points up and your thumb is the force. Okay, so all the positive charges experience an upward magnetic force as the bar is moving to the right. So that means that all of the negative charges will experience a downward force, and there's going to be a separation of the charges as it moves to the right. That means an electric field will be produced in the bar. The electric field always points away from the positive charges and towards the negative charges. Well, if there's an electric field, that means that the charges will experience an electric force as well. These positive charges want to go back down towards the negative charges. So what this picture is showing is that a positive charge in this conductor will experience an upward magnetic force and a downward electric force. And when these two balance each other, then we're going to have a potential difference created in the conductor. There'll be a balance where the charges will not want to move one way or the other anymore. So what we want to do is we want to look at this potential difference that's created. And this happens when the two forces equal each other. The magnetic force equals the electric force. Let's write down what we know for each force. The magnetic force is QVB sine theta, but we don't have to worry about sine of theta because the motion is perpendicular to the field, so theta is 90. If you remember in this equation QVB sine theta, that for the magnetic force, that theta is the angle between V and B. So if it's 90, this is equal to 1, and we don't have to worry about that. The electric force is the electric field times the charge. This comes from the definition that we learned that the electric field was the force per charge. So when we set these equal to each other, the charge cancels out. We need to make one more substitution. We also learned in a previous chapter that there's a potential difference between 2 points, let's say between this point and this point, that is going to equal the electric field times the distance between those 2 points, which in this case is given by L. Now usually there's a negative sign here, but we're just looking at the magnitude of these two forces equal each other, so we don't have to worry about the negative sign. We can solve for E here, and we get that the electric field is a potential difference per length. And we can substitute that into here. Let's see what happens. We've got the speed, the magnetic field, equals the potential difference divided by the length. Now all we need to do is multiply both sides by the length, and we get that there is a potential difference, delta V, that is equal to the length, the velocity or speed, times the magnetic field. That's going to be the delta V that is produced here between these two ends, between the positive and the negative.